Welcome, everybody. Today I'll be talking about our process of rebuilding our ML pipeline within Ray in the past year. So it'll be a very practical talk. So who here has done a recent large migration before? Past year? A few people? OK. OK, so we'll talk about our use case first. We work in the medical document processing space. So we get medical claims that come in from different sources. Our users are doctors, insurance companies, governments. And they upload large claims. They can be a few hundred pages long. Some can be in the tens of thousands. So what happens is that they upload this via API or through our claims analysis UI. It goes through our ML pipeline, where we classify, extract, and summarize key information. We feed it through a human-in-the-loop pipeline as well, because it is healthcare and legal data. And finally, our customers get it back, and they generate some kind of report or output out of it. So the challenge when we went through the rebuild is, how do we set ourselves up for success when we need to 100x our scale as we have more and more customers feeding more data in, as we add more use cases? So the company has evolved quite a bit. So I joined the company last year, but it's been around for a number of years. It started off as a platform to do medical document processing, and more features have been added throughout, adding more complex entities, more complex classification, adding summaries once LLMs came out, additional reporting, and adding different types of documents. And right now, we support over 1,500 types of documents. So actually doing inferences is not that easy of a task. It requires a lot of domain expertise, and the outcomes can be quite different. And the same document can have different implications for different customers. So when we went with the action of deciding to actually migrate our pipeline, we said, how are we actually going to do this? We have customers in production. They have tight SLAs in many cases, and Halloween just passed, but live migrations are definitely a valid costume idea. They are very spooky. So to go through our architecture, how we structured in the past, so before we had a very modular architecture where all the business logic, all the models, all the post-processing lived within a self-contained module. So that meant that whether there was some complex inference, some basic regex, everything was self-contained, and we used a shared library to actually pass data around. Now, this worked quite well when it was a simple pipeline, but as things continued to scale, it became more complex, and we were starting to hit performance issues. And all this was joined together with a custom events platform that became pretty unwieldy to coordinate. So the three main issues that we ran into was the inability to actually update modules in the manner that we needed as we onboarded more and more customers. It was slow to add new modules onto our pipeline without a centralized orchestrator. And we were hitting limitations of economies of scale. So the second version of the pipeline had a few main parts. The first one was an overlying orchestrator that tied everything together. So it would connect the pre-processing steps, the different models, modules, post-processing steps. So it would be our DAG orchestration. We then had our model serving layer, which is Ray. And we had a feature store for loading in specific features or files and documents as well. So we'd connect this all together, and each part had a specific responsibility so that we can update them at different points in time, since they all had different life cycles. So the way we use Ray is that each module called out to Ray when it needed it. Sometimes we used commercial LLMs as well. Sometimes we used mainly sort of straightforward business logic. But the core idea was that Ray would be responsible for everything, rather than in version 1, where it was self-contained within the module. So that allowed these modules to be very small and dynamic and have different life cycles. So why did we choose RayServe? The first reason is that we're standardizing in Kubernetes right now across the whole platform, both in the ML and application layer. So it meant fewer tools to learn. And as we spend time teaching engineers Kubernetes, right, all those patterns could be reused at the ML platform level. The second reason was we had heterogeneous models, meaning that some models were served on CPUs, some on GPUs, some used one architecture, others used others. And it didn't make sense at this point to standardize, for example, on something that only compiled to CUDA as our main source of inference. And finally, there's a lot of additional things that Ray provides. If you've used Ray in production, you have some good auto-scaling capabilities. You could use fractional GPUs to get some speed-ups for lower volume requests as well. And you also have the ability to go from batch and online. So that's something that we took into consideration as we were building the platform, not just for the next few months, but for many years. So I'll start off with the outcomes. So this migration has been a success. From a developer perspective, we reduced the number of lines of code by 50%. Keeping 100,000 lines of code in our brains was very hard, split across 15 different repositories. So that's a win from a productivity perspective. And from a bug perspective, it's much easier to reason and understand. And if you've been using AI coding agents, having everything in a monorepo with a smaller code base makes productivity also much faster. We reduced our processing time quite a bit across files as we were able to leverage the capabilities of a single serving layer and decoupled modules from models. And finally, because of this disaggregation, we could also increase the max file size. So for whenever our customers sent us hundreds of thousands of pages in one PDF, we are ready. So to go through the repo structure, because I think this was actually conceptually one of the really interesting things to do, is how do you actually design a pipeline and how do you map it to code that developers use? So we decided to go with a monorepo approach. It was very easy to link through different modules, traverse it. If there are any side effects, they're easy to find. We found some interesting bugs when somebody forgets that they updated something in one module but not the other. We had some shared logic modules as well. We had specific modules dedicated for our orchestrator. So if we wanted to swap orchestrators for whatever reason, it'd be fairly easy. We had our serving layer with Ray. And then we had CI/CD and everything else. So this is roughly what it looks like. It's simplified a little bit. So we had these different modules there. Now, what we also did is we had multiple services, and they all had their different deployment patterns. So the serving layer had different deployment patterns. The actual Ray applications also had different deployment patterns, and our modules as well. So when we're actually doing CI and CD, we wanted to make sure that we weren't just shipping this massive 50,000 lines of code of monolith. We could actually deploy where it made sense for developers. So developer productivity was really, really important. And finally, as we were saying, we're Kubernetes native, so we're using Argo to deploy all these different components and do various checks, like do we actually need to rebuild a package in the monorepo, do we not? How do we actually schedule it across different environments, and using config with pull requests so you don't just go into production and break something or make a change that's not trackable. So I'll go through and talk about our Ray setup a little bit with some practical examples. So we used three main components here. The first one is we used Ray serves multiplexing capabilities. The second one, we used multi-deployments and apps. And the third one is that we deployed multiple clusters with the KubeRay operator. So with multiplexing. So we had a number of models that were very similar, whether for different customers or very similar architectures. And it didn't make sense to just serve them as separate workloads. So Ray served multiplexing. It was a nice addition. It's a few hundred lines of code, but it means that we don't have to write this concurrency or state management ourselves to do the routing. So whenever a request comes in, the Ray router would try to route it to the correct worker or actor in this case. And that'll allow us to gain some benefits as we scale up. We load in a larger model, let's say if it's a base model, and then we can load up all the adapters. And then we can actually load balance across different actors and clusters doing this approach. Now, one of the limitations right now, and if you've worked with Ray Serve, is that there's actually no good way to initialize these models across the clusters. So we actually did some random initialization because we couldn't say put model A on this actor, put model B on this actor, and C on this actor. So there's actually some interesting logic on how do you initialize based on your predicted requests that'll come in. And as we were going through, we were tuning in the link at the top where you specify how many multiplexed models you can have and their instance count. That also requires tuning whether you scale within the actor itself or outside of it. The second idea was how do we actually do deployments? So within Ray, we can have multiple deployments that exist and pass state between different models. And we did this with the idea that sometimes things would be reused and sometimes they wouldn't. So we had multiple applications that were being deployed, and we had pre-processing steps. For example, how did we handle images versus text would be different. So we had different preprocessors, but we want to reuse that logic depending on the model combination. And the whole idea was that we wanted to group things in a way where we had similar life cycles, so that if you had application 1, that would be updated every 3 days, and application 2, that would be upgraded every month. You didn't have to update everything every 3 days, right? It doesn't make sense. There's more risk with the deployments. And we had to organize our clusters to follow this pattern as a result. So the way that KubeRay works is that it brings up a cluster of the actors for our applications. And when you deploy a new version with actual code changes, you deploy another cluster and then switch the load balancing between the two. So again, this goes into the whole idea of how do we actually choose our deployment cycles and map applications within clusters. So for example, we had one set of applications that extracted entities. We said we're going to deploy them in a similar life cycle, so we'll group them in one application. Now, if we group them all in one cluster, we'd get some benefits for simplicity of the code base a little bit. We'd have better utilization of the underlying hardware. But in this case, we chose developer productivity as being more important than necessarily getting a little bit more GPU utilization. So going back to the results, these are sort of the comparative aspects. So we could deploy a lot more models using this new architecture. People weren't scared to go into the code base and make changes. So that allowed us to iterate more quickly, both on the training deployment side, doing A/B testing as well. And because we had a centralized way to deploy models, it wasn't going into different code bases and repos and making the changes there. You just went into the Ray serving part of the code base and made your change. This allowed us, as we onboarded more and more enterprise customers, to actually focus on training customer-specific models and have cleaner segregation there. And finally, as we deployed more and more models, we got better results because of that. And with the more modular nature, we could actually do better unit tests. We can test the model results for accuracy, latency, and so forth. And it wasn't just redoing all this logic across every repository. So the next part of the talk, I wanted to talk a little bit about testing and migrating our application. So there are a few important lessons here or considerations to take into account. The first one is that we need to have a zero downtime rollout between our first version of the pipeline and the second. The second one is that different customers had different expectations and different tolerances for us for turnaround times for various SLAs. So we used feature flags to migrate different customers across the board. And finally, something that's really hard to do with unit tests is that it's really hard to catch 1 in a million issues. So we had to figure out a strategy where some customer uploads a weird PDF that is 800 megabytes large with a 20,000 by 20,000 pixel X-ray image that you might have never encountered in the past, unless you went through all the inferences at once. So talking about the rollout strategy, so we have a multi-region approach based on where our customers are. So we started off with one region that was the lowest risk one. And what we did is that we deployed our pipeline v2 in shadow mode, meaning that all the requests went to that pipeline, but none of those requests or results were routed back to our customer. And we slowly ramped the volume there from a small number of customers all the way to matching the production volume. Now, the reason for this is because the pipeline is quite complex, so we wanted to make sure that we had a close to 0% error rate and the results matched. And then came various phases. So we did bug fixes for almost a month where we caught hundreds or more than 100 bugs along the way, very niche issues that people haven't seen in years or popped up with new file types. So this is pretty interesting to see in the wild, where you run a pipeline clean for 7 days, and then suddenly somebody uploads something pretty phenomenal. Then we divided our customers into different segments. So we had the lowest risk customers that we would transition to pipeline v2 first, then a second group, then a third group. And then finally, once all the customers were live in production and we had v1 running in shadow, just in case we needed to recover a file, we turned it off and had pipeline v2 as our primary run. And then you rinse repeat this in region 2. 3 and 4 and so forth, but hopefully it's much easier because we know that we've eliminated many of the integration issues, we've caught many of the edge cases we've seen before, but you will see different types of files in different regions, so you'll keep seeing errors. So with this migration, the goal was to do it somewhere between an MVP and a full product because there were so many gains to be had from doing the migration. But there's still a lot of opportunities for us to continue to optimize. The hardware is a huge area. We're in the process of updating the types of compute that we're using to save some costs, choosing the different GPUs that we're using based on scale and cost as well. Looking at where the actual bottleneck analysis is, so this would be a whole other talk of how we actually orchestrate and time out results. And finally, continuing to tool our auto-scale rules to make sure that our turnaround times and costs match customer expectations. Now, I want to go through an interesting bug. These are always fun to get into the weeds at a technical conference. So one of the problems we solve is called PSS, which is page stream segmentation. You can see on the left here, you have some kind of stream of pages that come in from a PDF, and you want to say which one is the start of a new document. So here I've drawn these lines to indicate where the pattern changes. So you have a cover page potentially, and then subsequent pages. So we do this with a binary classification. If it's a new document, it's a 1. If it's an old document, it's 0. And we were unit testing our pipeline v2, and it looked great. And then we deployed it into production, and it was not great. So we tried to figure out, it took us a few weeks, what was actually going on. Because why don't the unit tests match production? And the reason was how we were actually allocating our models. We had to do a deep copy on Ray and actually reload the models in a different way than we did in PyTorch. And this was the interaction between multiplexing and our actual model. So these are some of the things that get you if you don't go into the details of the framework and actually understand how serving is being implemented. So again, the lesson learned here is read deeper into the abstractions, understand what's happening, but you're going to run into these issues across the board. So then came the decision. We're serving mainly classification models and smaller models. Should we actually serve LLMs within Ray? And what we realized was that our workloads, well, we knew this, are very spiky across the board. And we knew that open source models were evolving very quickly. So rather than focusing on that, we focused on implementing our cloud APIs. And that allowed us to do things like testing models much more quickly and not focus on serving. So to maintain the velocity of the team, the costs, and the stability of APIs, we deferred this to another project. So finally, we're going to continue to upgrade our models. We're going to do more online serving in production and continue to change our auto-scale rules as we grow with volume. And as always, every project you have a lot of reflections, so all good software engineering patterns that you have to consider. And we're going to have a blog post come out soon at the end of November with our full learnings. So thank you, everybody, and happy to take questions. Yep.
Hey, can you raise your hand if you have a question? I'll give you the microphone. Thank you. Thanks for the talk. When you're using multiplexing, are you mostly using it to swap out the LoRa adapters? And if you are, how many adapters do you guys have? And what's the switching cost between adapters?
So we have LoRa adapters. We have also just additional layers that we fine-tune on top of the model. We also have models passing responses to other models. So they're in the dozens. They're not that much, but the main limitation was serving, and now that we're removing that limitation, we can train a lot more adapters. So.
Cool. Any other questions?
So it looked like the model serving workloads were also making calls to feature stores or potentially third-party LLMs and stuff like that. Were there any scaling challenges, kind of mixing the CPU-bound workloads versus the I/O-based ones to call to external services?
Yeah. So when we were doing actually image splitting and S3 work, we ran into this bug where we naively parallelized things, but then actually had to rewrite that module because opening up 1,000 concurrent connections to S3 is a bad idea. So you want to open up one and then batch things through that. So we actually wrote almost like some map-reduced logic in our orchestrator to do that effectively and do micro batches with S3. So it wasn't purely like a functional parallelization paradigm. So we ran into those gotchas all across the board.
All right, let's give our speaker one more round of applause.